Welcome to our last, summary video on the calculus topics for the further math course. Not sure if you've viewed many of the others. I know that by reading the text and based on your memory and how comfortable you are coming out of BC last year, you may not have really needed any of these types of review videos. Here, once again, I'm going to take several topics together and just provide a summary and some examples of some maybe of the newer ideas. This final topic is about differential equations. Once again, if we go through the different sections, we talked about the limits and continuity, we move to the differentiation, we then move to the integration, and now another big part of the calculus is differential equations. I've stated before that for many of you, you may take a course in purely differential equations, which you'll learn these techniques plus many, many, many more. Up to this point, this is what we have. I would call a simple differential equation just something that you recognize that in order to find the original function, you just need to integrate. We may need to separate the variables before we integrate. Sometimes this leads to a simple integration, sometimes very complex. Once we get that differential equation solved, it can be a general solution with a plus c, or we can find the particular solution as long as we have some initial values or some values about the specific function. We can identify and pinpoint the c. So that kind of goes with all of these. Now, with just differential equations in general, here are some of the different things that we've been able to do. We know what a slope field is. A slope field is just a field of the slopes. It's these little marks that when you stand back, you kind of see a picture of a solution to a differential equation. We've used Euler's method before. Euler's method is a numerical method, an iteration method, that allows us to find the solution of a differential equation or approximate it. We've also had in the past to translate expressions to differential equations. One of the most basic was the rate of change of y is proportional to y, which led from y prime equals ky into our nice y equals ce to the kt exponential growth function when we solved it. A newer idea is this idea of isoclines. And basically, if we take a look at a slope field or any differential equation, they don't have to be lines, by the way. They're basically a figure or the equation of all of the different points that would have the same characteristic or same slope. As a quick example of that, if we look at this one, we notice, for example, that this derivative does not exist when the denominator is 0, which leads to y equals x minus 2. So the line y equals x minus 2 all of these points would share the solution here. Likewise, if this happened to be 0, we'd have x squared plus y squared equals 1, which we know is a circle centered at the origin. So for that, if we had the slope field superimposed on both of these, this would be the isocline for the 0. The line would be when it's undefined. And there could be others. So that's something, it's kind of minor, but it is a word that it's not hard to understand. So there that is. Now, the big things I want to focus on are the ways to solve these differential equations that we would consider just not simple. And the first of these was an optional topic in BC, and they were called homogeneous. Basically, let's say you had trouble separating the variables, or you couldn't, and they were in a very specific format. Well, what we tried to do with these homogeneous ones, and this is an example, if I try to solve for y, separate the dy and dx, I'm just going to have some trouble. So what I would do is I would let y equal vx and go from there. Now by saying y equals vx, we then have dy dx equaling the derivative of vx, which is the derivative of first, which is dv. Make a change on this. Let's differentiate with respect to what x, so it's dv dx times 1, x plus the derivative of the other one times the first. What's going to happen then is we're going to be able to replace dy dx with all of this. And then with that situation, we should be able to separate the variables. We get x plus now 2 dx over x. So we can see we're going to be able to do this. I'm not going to continue this example, but we can now solve it in terms of v and then make our nice v equals y over x substitution and get our solution that way. So they're homogeneous. They're in a very specific format when we can't really solve it. Many times we're kind of prompted to use that type of a substitution. But again, that's partly review if you took advantage last year of the optional topic in BC. The next one I want to look at, which is the real new one, and that is using something known as the integrating factor. And in this case, we have a form where we have a differential, a derivative, plus some function times y equals another function in terms of x. And when we see that format, a substitution we can make, and we call it I for integrating factor, is e to the integral of the p of x. Now, this may seem a little arbitrary, and of course many of these methods are on the surface, but they work. And that's one of the things that differential equations really teaches us, that we identify a structure. From that structure, we identify a method, and then we carry that method through and we solve our differential equation. So let's see what happens with this one. If I'm given this equation and I kind of compare it, we can see that this is going to be my p of x. And if that's my p of x, my integrating factor will be e to the integral of 3x squared. Well, the integral of 3x squared is x cubed, so it's e to the x cubed. Now, this is the big step once we make that substitution. We are now going to multiply the original one, the whole differential equation, by that e to the x cubed. So let's see what happens with that. Well, we get e to the x cubed dy dx plus 3x squared y e to the x cubed equals 6x squared times e to the x cubed. Now at first this looks even more complicated, but there is something that we can notice. This is the result of the product rule of some derivative. If we think about it, what would that be? Well, it looks to be y times e to the x cubed. So all of this in purple is nothing more than the derivative of y times e to the x cubed. And let's kind of work backwards to make sure that works. It'd be dy dx times e to the x cubed plus y times the derivative of e to the x cubed, which is e to the x cubed times 3x squared. And so now if I want to solve this differential equation, we can just integrate both sides. Now I'd get the dx over here, put a dy just to make it look a little bit better. Well, I don't even have to worry about that. And so now what we have is, of course, this integral is going to be itself. The integral here, if this is u, this is du, so we're basically integrating e to the u. So of course that's just e to the x cubed. Of course we have plus c. So if that's the case, we have y e to the x cubed equals e to the x cubed plus c, and I think I might have to have a 2 here for an adjustment. Yeah, because the derivative would be 3. So we'd have 2 e to the x cubed. And at that point, we can go ahead and divide everything by e to the x cubed. Could, of course, call that c e to the negative x cubed, however you'd like it, but there's our general solution. So it's known as the integrating factor. So m, n, and o basically deal with differential equations. We go from pretty simple ones with some of these review kind of connections to our differential equations. We then review some homogeneous differential equations, and then finally working with getting experience with these integrating factors. The integrating factor and the homogeneous, have some consequences. We let y equal vx. This is an automatic consequence, and we go with it. Once we choose what the integrating factor is going to be, in other words, we need to know the p of x, again, everything flows, but a big part of it is once you get the I of x, you're going to multiply both sides of the equation or the whole equation by that I of x. What that should do for you, and this is when you know you're on the right track, is you should be able to identify some of it as basically a derivative of a product. And as long as you can figure out what those two functions are that are being multiplied together before we differentiate, we can then integrate it, which is back to the original. We just have to integrate the rest of the function. Now the final thing I have up here is the last thing in P, the nth term Taylor polynomial on approximation. This is a nice, way to kind of connect something we had done earlier in this unit, and that is working with Taylor polynomials. So much of solving differential equations is about deciding, can I do it explicitly or exactly, or is there more of a numeric approach that makes it either possible or just more convenient. We've already had Euler's method that was one of those numerical methods. Doesn't mean we couldn't solve a differential equation exactly and procedurally, but many times it would suffice just to use Euler's method because of the iteration part to it. Same thing with others. We might be able to solve a differential equation, but many times all we really need is a certain degree Taylor polynomial. So there's a nice example on these Taylor polynomials somewhere here. It's example 57. And I'm just going to point that out for you to study. But it's a nice review of creating the Taylor polynomials. It will show you maybe how close it would be to the actual solution, and part of that example is also to get the exact solution. So that's the short video on wrapping up the calculus topics. I will post yet another set of problems on M through P. That collection of 4 different problem sets would be a nice review for all of the calculus that either we've had in the past or that could be expected if we were to take the further math test. To finish out the year, I'm going to have a few videos and review or extensions on some statistics topics. And then ultimately, I am going to post an actual IB test just for some closure and to give you some confidence that you have picked up a lot of these kind of interesting topics from mathematics over the last year or so. So enjoy the weekend, and thank you.